here we are with this target function, this loss function. What does that mean if y is multivariate? So the target label has 4 labels, and we predicted 4 labels. We know how to subtract 2 variables, right? What is a vector minus a vector? It's another vector. How do you square a vector? Well, at that point, usually what people do is they say, oh, we'll just say it's element-wise. So we square each element, and then we sum them all up. And that's kind of how we implement sum squared error with multivariate labels. So yeah, it is a little bit implicit. Essentially, we perform any operation that we don't know how to do to a vector element-wise, and it just makes it all work out. In the sense of backpropagation, here's what that does. That means that you've got these output units here on your neural net. And there's a bunch of preceding layers, bunch of weights. Good enough. Copy these and paste them here too. Okay, this is like unto a neural net. Well, let's suppose there's some amount of error that's occurring right here, and some tiny amount of error here, and some medium amount of error here. The neural network has to, say, adjust this weight. But if it makes this weight bigger, it might make this error worse and that one better, right? There's compromises going on. What's the neural network going to decide to do? Well, this is the biggest one. The biggest error is right here. And it's trying to minimize the sum of this thing squared plus that thing squared plus that thing squared. The minimum of that happens when they're all kind of the same value, right? And as small as possible. So what it's going to do is end up adjusting this weight in the direction that makes this output better, even if it makes these two a little worse, because overall that makes sum squared error better. So the long-term effect is when you minimize sum squared error summed over all the labels, it tends to put equal priority on all of the predictions. If for some reason, say, this label is really, really important to you, and this one you hope is right, but if it's not, that's okay as long as this one's right, then what would you do? Well, you change your target function. You basically say that instead of summing over all of the elements, maybe you take 100 times this one, or take this one squared times 100 plus that one squared. And then if you were to derive backpropagation for all of that, it would then focus on making this one correct and put 1/100th less energy into making that one correct. Does that make sense? Okay. Now, okay, I talked about this and I'm feeling like I want to move on, but I want to check with you. It's really okay to say, no, I think I'd benefit from you going through it very slowly and taking time to get your minus signs correct. Do you guys want me to take the time to get my minus signs correct, or are you content that I've taken you far enough that you can just do the math now?
I have one question.
Yeah.
The thing that always messes me up is when you update the weights, it's the weight minus the learning rate times the gradient, but then you can get rid of the 2 and the minus because that's part of the gradient. I hear about that.
Okay.
It's just that last thing.
This 2 is multiplied by the whole thing, right? Because of that, if I were to adjust my learning rate, it'll absorb the 2. Okay. The other deal is, do you add or subtract this thing? Well, remember we've been dealing with equal signs, and that equal sign says this thing is the very same as that. So we're going to subtract it. I think those are the only issues. Did I cover them both, or is there anything else? Okay. An alternate form of the same equation that I could ask you very well on the test is, here's a picture of a neural network. Here are some numbers. don't know what numbers I'd give you. I'd say predict the activation of this neural network. And I kind of did that on midterm 1, right? Okay. If you remember backprop really well, and the math and the algorithm should come out to be the same, but let's do it from a second perspective just so you have 2 witnesses of how to do it. What's the first step? Here's your feature input. What do? Usually we assume that this first set of circles represents the input values themselves, so I'll stick them in these circles. I'm going to say the first thing we do is multiply by the weights that are represented by all these lines. So this is really a vector times a matrix. And this will produce a vector of output that I'll draw a square right here and say that square represents the vector of output that comes by multiplying this vector times that matrix. Okay? Then we're going to element-wise run this vector through the activation functions, which are represented by these circles. So we take the tan h of each element. Then we're going to take this vector and multiply it by all of these weights to obtain a net vector here. Then run it through the activation functions. And the result is the activation of the output layer, which is what we say is the activation of the whole neural network. That's the forward propagation step. And this should be very familiar to you. Presumably, we have some targets, which I will draw a red square and say I have now represented the targets. And the difference between these green squares and those red squares is your error signal. That is not the same thing as your target function, right? If your target function is some squared error, do you put the square of the differences between these values as the blame on the output layer? No. That's not the same thing, right? If you, how can I explain it? Just don't do that, okay? The target function answers the question, how do you change, if you change this weight, how does it affect the difference between the fit of the model and my data, right? That's not necessarily this blame term that we're putting on the output units. The blame term is computed by backpropagation. It's not the target function. I don't know how to explain it except to just say it again. Don't put the square of the error as your blame on the output units. The blame on your output units is the difference between the target and the prediction. How do we know that? Because backprop says so, because we derive it. Okay? And by the way, that alone is not sufficient. That blame is just a term. It's part of the equation of the gradient. So if someone were to ask you, what is blame exactly? What is blame exactly? It's incomplete math. The complete math is the very last step when we finally take the input times the blame, and that product is the gradient for that particular weight. It just happens that the gradient for all of these units in the whole neural network, they all have a whole lot of things in common. And so we call those common parts blame because it's a term that if we compute those terms, then all the math gets really, really simplified. So the whole reason we do this blame thing, blame is not even a thing. It was invented because there's so much similarity in the math. For example, look at this thing. Nasty, horrible, scary equation, right? But if you look closely, this part looks exactly the same as this part. And if you were to just replace that with, say, the term blame, then this equation would suddenly look really, really easy, right? That's why backpropagation is what it is after you simplify all the equations by putting these common blame terms in, then it turns out it's not so bad. So you take the target minus prediction, and that's just the blame on the outputs, which is not the same thing as the target function. And we're going to compute the blame on all of the units in the network. So to compute the blame on this hidden layer, we take the blame on the output layer. And wait a minute, I forgot a step. That blame that we have on our output layer, This is the blame of the output of our activation function, right? But we need to know the blame on the output of that linear layer, because that's the layer before our activation function. So we get it by taking that blame here on the output layer and multiply it by the derivative with respect to the values that came in of the activation function.